In this video, we're going to prove the quotient rule. So I've written here two forms of the quotient rule. One is in terms of u and v, and the other one in terms of f of x and g of x, right? So the quotient rule states that the derivative of a function divided by another function is equal to the derivative of the first function times the second function minus the first function times the derivative of the second function over the second function squared. Or u prime v minus v prime u, or u v prime over v squared, right? And we can write it in this form as well, f of x divided by g of x. So as you can see here, h of x is a composite function because it is comprised of f of x and g of x. So it's comprised of two other functions, right? It has two other functions inside it, which means h of x is composite. So the derivative of the quotient of two functions is expressed using this formula, using the quotient rule. So I would like to prove the quotient rule using the definition of a derivative. Now, the definition of a derivative, f prime of x, f prime of x, or dy over dx, the derivative of y with respect to x, is equal to the limit as h goes to 0 of f of x plus h minus f of x over, I'm going to use a line here, over h. Okay, so this is the definition of a derivative, right? It's basically the slope. It's the slope of the tangent to a function. For instance, we have a function, let's say a quadratic function with positive coefficient of x squared. So the x squared has positive coefficient. Let's say, okay, I'm gonna move this down a little bit. Okay. Say I have a quadratic function. So the general form of a quadratic function is y equals to 8x squared plus bx plus c, right? Now say a is positive. A is positive, then it opens up, something like that. So this derivative is the slope at any given point of this graph. Say this point, so we can draw a tangent at that point, and another tangent at another point, or another point like that. So these are like, points, this point, this point, this point, like that. So that's the idea behind the derivative. The derivative is nothing but the slope or the gradient of the tangent at that point, right? So using this definition, we're going to try to prove the quotient rule. Okay, so we're going to find the derivative of h of x, right? Now, using this definition of the limit, derivative of h of x, actually not the definition of the limit, the definition of the derivative using limits, okay? I'm sorry. So the definition of the derivative using limit is the limit as h goes to 0 of f of x plus h. Now if it's h of x plus h, it would just be f of x plus h, like this, over g of x plus h, right? G of x plus h minus h of x, which is just f of x over g of x, over h, right? So this thing's equal to limit as h goes to 0. Sorry. As h goes to 0 of, let's see here. I'm going to try to make this whole thing into one fraction. Okay, so I'm going to cross multiply. I'm going to make the denominator the same. So this is going to be f x plus h times g of x minus f of x times g of x plus h over since over the denominator, the new denominator is g of x times g of x plus h, right? But then the whole thing divided by h again. So the h is going to come here. The h is going to come here. So h times g of x plus h times g of x. Right? So this is equal to, let's see the top here. Okay, so what I want to do here is I want to make this sort of look like the form here. So f of x plus h minus f of x. All right, I kind of want to make it into that form, right? So what I can do here, I can take out this one. For this one, I can take out, let's see, I can take out or factor out h goes to 0, g of x. So if it factor out g of x from here, it's just going to be like that, right? Times x plus h. But what I want to do here is I want to write, since the definition of a derivative using limits is f of x plus h minus f of x. I want to write this form here. Okay, so I'm going to write minus f of x there. Because there must be something to do with it, right? So I'm just going to leave it like that first. So let's see. Minus f of x times, same thing here. So g of x plus h. G of x plus h times, no, not times, sorry, minus g of x, right? Okay. Now we have that over this whole thing over this whole thing again. H times g of x plus h times g of x. Okay, now what will this give us? Limit as x goes to 0. Now this, I can rewrite this since there's a g of x here. Oh wait, sorry. Okay, so the g of x is here. I thought there was another bracket. So in this form, we can do is, I'm gonna take these out. So just imagine that, okay, I have an idea. I'm gonna cut this, I'm gonna rewrite it. Okay, so basically I just wrote this bottom part over here, so I just separated them. Now in this case, it looks clearer, right? That we can rewrite this whole thing into independent limits, or independent terms, my bad. Independent terms, right? So it's going to be g of x times f of x plus h minus f of x, okay, over h. Over h. Now this whole thing minus this thing of x, or you can write the limit as well in front of this. It's the same thing, using the rules of limit. Okay, I apologize, the video was cut. So what I was saying was you can write limit as h goes to 0. You can also write the limit here, the notation for limit, as in like limit as h goes to 0 of f of x times g of x. It's optional, really. Minus g of x. Yeah, like that. Over h. Over h, right? Yeah, so this basically means the limit of this minus the limit of this. So you can write it here as well. Limit as h goes to 0. Or if you don't write it, it's also fine. Times, oh wait, now this whole thing, okay, this whole thing, just so it doesn't confuse us, times 1 over this, oh, sorry, times 1 over g of x plus h times g of x. Right? I'm going to scroll it down. Okay. So this whole thing, we know that the limit as h goes to 0 of this is just f prime of x. So I can rewrite this as g of x times f prime of x. Minus, and this, same logic. This whole thing, actually, I can just, this whole thing right here, I'm going to mark it, is g prime of x. This whole thing f prime of x. This whole thing is f prime of x. And that's g prime of x because we're doing this in the context of limits, right? So g prime of x times f of x. F of x over that thing right there. Now, since it's the limit of everything, right? It's the limit of everything, so that means there will be a limit sign here as well. I apologize for that. So there will still be a limit sign there. Limit as h goes to 0. So the limit as h goes to 0 of this whole thing, g of x plus h times g of x. Now, in this case, as h goes to 0, if you plug in h here, then this would just become 0. This term, this h term would just become 0. So it's the bottom, or the denominator, is going to be gx whole squared, g of x whole squared, right? So I'm just going to rearrange this and make it look neater. So f prime of x times g of x minus f of x times g prime of x. Okay, I'm going to write the minus sign a little bigger. Oh, sorry. Okay. Over, right, over g of x whole squared. And there you have it. This is the quotient rule. This is h prime of x, which is the derivative of a function divided by another function. F prime of x times g of x minus f of x times g prime of x over g of x whole squared. Right? Derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. And that's how you prove the quotient rule using the basic definition of a derivative in limits. Now, I'm going to show you how we get this. So how I get this actually, this is the definition of a limit, right? Oh, I'm sorry. I mean the definition of a derivative. So imagine that we have a line. I'm going to draw a line. Okay. So this is my line right here. This is my line. And The derivative is a slope, is none other than the slope of the tangent to that function at any point. So imagine that I have a point here. Okay, I have a point here. Let's say this point is x comma f of x, x comma y. What about this point right here? So I just want to plot two arbitrary points along this line. This point would be x plus delta x, comma, well, the y would just be f of the x, the x, right? So it's gonna go like that. So this is the other point, the coordinates of the other point, and this is these are the coordinates of this point. Now, in order to find the slope m, the gradient basically, this m is equal to delta or delta x, right? So delta y or delta x. Now, delta y in this case is a change in y. So it's this function right here, f of x plus delta x minus f of x over the change in x, which will be x plus delta x minus x, which will just be, so since the x's will cancel, we're just going to get delta x at the bottom over delta x. Now, once we're here, once we're already here at this stage, what is the definition of a derivative again? Imagine that these 2 points, they come closer to one another, like as close as possible, and they sort of like you know, I'm gonna draw another line. So let's say the points they get closer and closer and closer to each other, and they become so close that they don't meet, but they become infinitely close to one another, but are not touching. So that means that the delta x approaches 0, right? As they go closer and closer and closer and closer, delta x approaches 0. So you can take the limit, right? So the definition of derivative, dy over dx, the derivative of a function y with respect to x, is equal to the limit as delta x approaches 0. As delta x approaches 0 of this thing, of the gradient, basically. So f of x plus delta x minus f of x over delta x over delta x. And there you have it. So if you can, if you replace this with h or a or anything really, so h or a, then we're going to have the limit as x as h goes to 0 f of x plus h minus f of x over h. And that's the definition of a derivative using limits, or the very, very fundamental definition of a limit. Sorry, of a derivative, not a limit. So this is the fundamental definition or concept of a derivative using limits. Thank you. And I hope this video has been helpful for you.